Okay, let's look at exponential growth and exponential decay, right? So when you have exponential growth or decay, the differential equation goes like this. The rate of change of quantity P, you can think of it as like a population of bacteria or something like that. And the rate of change of the population is proportional to the population itself. Right, so this is a typical equation we get. All right, then initial condition is, let's say at the t equals 0, initial population is p0. Right, so we can solve this equation, and this equation is called the separable equation, since we can separate the variables, all the p's on the left and maybe all the t's on the right. Right, so let's do that. Alright, so first thing we do is we're going to try to divide both sides by p and multiply both sides by dt. Alright, see what happens. Alright, so divide by p, so you're going to get the 1 over p. I have dp. Right, so this is equal to, right, so multiply by dt, so you're going to get the k, right, dt. Right, so you can see that all the p's is on the left hand side and all the t's is on the right hand side. So that's why this is called the separable equation. Maybe I should say separable equation. Alright, and then what you can do is we can put the integral sign on both. So we do the same thing to both sides of the equation. Right, then integrate the 1 over p with respect to p, so that would be natural log of absolute value of p, right, is equal to, right, so k is a constant, so antiderivative of a constant is with respect to t is kt, and plus some constant. I'm going to use c1 because I want to be able to use the c later, so I call it c1. Alright, so in order to simplify this, I'm going to raise e to both sides. Right, so you have e to the natural log of absolute value of p, right, is equal to e to the kt plus c1, right, and I'm going to rewrite it this way. So this is going to be equal to e to the kt times e to the c1. Right, e to the c1 is a constant anyway. Right, then we can cancel e and natural log, because exponential function and the log functions are inverses of each other. So when you compose, they basically cancel out each other. Right, so we end up with just the absolute value of p. Right, so instead of writing absolute value of p, I'm going to just put the plus or minus. So p is going to be either plus or minus. Right, I'm going to write this guy first, e to the c1, that's just going to be a constant, and then you have e to the kt. Right, then since this is just a constant, plus or minus included, this guy is just a constant, so I'm going to just call this constant the c. Right, so this is going to be just simply some constant. It could be negative, it could be positive, e to the kt. Right, then we can use the initial condition when t equals 0, value is p0, so I'm going to just do that. So p of 0, if you plug it in, right, so it's a c times e to the k times 0, right, but e to the 0 is 1, so this guy right here is 1. So this is equal to C, which is supposed to be P0. Right? So therefore, we found the population function, you can think of it as P of t, which came out to be just P0, right? E to the kt, right? So this is the population function, if you think of it that way, right? And I just want to mention, you know, when k value makes a difference between the growth and decay. So when you have a positive k value, it's going to be exponential growth. So when k is positive, you have exponential growth. And when you have a negative k value, then you will have exponential decay. So when you talk about you know, bacteria population, it's usually k value is positive, so that we're talking about population growth, right? All right, so that's the kind of solving the differential equation in general. All right, so let's look at a couple of concrete example. All right, so if you have this equation, so in this case k value is 2. So what you have is, so this one, it's going to be y is going to be equal to, in this case there's no initial value, so we're going to leave constant as c, and a k value is 2, so it's going to be e to the 2t, right? So this is the solution of differential equation, right? And how about this one? So if you have dy over dt equals 2, right? So this is a k value. Sorry, this was the k value here, right? For this problem, k value is negative 0.5, right? Then we have initial value. So this is basically our p0. Maybe I should call it, since the function's name is y, so I should probably call it y0. Right? So the solution is going to be y is equal to, right, initial population or initial value is 100, e to the, right, k value is negative 0.5 t, right? So this is the particular solution of this initial value problem. Right? All right, so that's it. I hope that this was clear.